Lesson 16 is about adding and subtracting polynomials. Before we get into the addition and subtraction, first I want to just talk about what a polynomial is because it could be a new word. So 16.1 is just getting into what is a polynomial and then what are the rules for them. So starting in the upper left corner, a polynomial is an expression with multiple terms. In some cases it's just one term, but more so than like what a polynomial is, there's some stricter rules on what a polynomial isn't, or like what can't happen in a polynomial. So right here, this 9x to the fifth plus 2xy squared plus y plus 7, that's an example of a polynomial. It's an expression, like no equal sign. It's an expression with multiple terms, and terms could be a new word. It could be a word that you hear sometimes, but like you're not exactly sure what it is. So in this case, terms are just kind of like pieces of the polynomial that are separated by like a plus or minus. If it has a minus in front of it, it would just be a negative term. So right here, like the 9x to the fifth, that's one term. 2xy squared, that's another term. Y is another term, and then the 7 is its own term as well. So this one has 1, 2, 3, 4 terms in it, and notice all those terms are separated by plus signs. Like I said, if we had like a minus in there, then that would just make it a negative term. Okay, so almost like maybe more, arguably more importantly than what the definition of a polynomial is the set of rules that polynomials need to follow. So polynomials have a set of rules starting on the right side of the page. The first one, the first bullet point is that the exponents of variables cannot be negative. So for example, let's say I have like an x to the negative second power. That would mean that it's not a polynomial. So that's no good. Like obviously like negative exponents, they can exist. Like we've already gone through like a whole unit on negative exponents, but they can't be a polynomial. Breaks the rule. And then the second one, exponents of variables must be whole numbers, like no fractions or decimals as exponents. So if I have, say, x to the 1/2 power, that's no good because the exponent is 1/2. That's not a whole number, it's a fraction. Notice how so far both of these have said exponents of variables, that should have an S behind it. But anyways, it's only like regarding the exponents on the variables. So for example, like if I had say 4 to the 1/2 power, like that's a fraction exponent, but it's not over the variable. So since it's not over the variable, it's okay. So it's just only that like little part that's kind of snuck in at the beginning of exponents of variables, like that's very important that we're just like creating rules around the exponent on the variable. Okay, so the third bullet point now, if the terms of a polynomial include a fraction, so if you have a fraction within your polynomial, like the whole term, there can't be a variable in the denominator. So like if I had 4 over, say, x squared, I can't have a variable in the denominator, so that would make it not a polynomial, but like I can have fractions. That's okay. Like let's say I had the other way around. I had x squared over 4. In this case, I don't have a variable in the denominator, so it's okay. It doesn't break any rules. That one would be okay. If you see the variable in the denominator of the fraction, that would make it not okay. Okay, so moving down this little graphic, so these are just kind of like different types of polynomials. So if we look at just the first box, like the kind of reddish one in the upper left, you can see the title of this box says single variable polynomials. That means it's a polynomial with a single variable. It only has one type, so basically one letter. So you can see on the first one, 1 minus 25a to the fourth, it only has an a. It's just like that's its only type of variable, so it's a single variable. If we look at the second one, like there's the x squared and the x, so 3x squared minus 10x minus 8, they have like the two different x's, but it's the same letter, so it's the same variable, so it's okay. So it'd still be a single variable polynomial. And then if we move to the upper right, kind of like the turquoisey one, this one's titled multivariable polynomials. So that means it's going to have more than one variable. So like if we look at this expression, it's ab minus b squared plus 11a minus 4. So you can see like there's two different types of variables. There's these a's and then there's these b's. There's two letters, two variables. And then same thing in the second one. So xy to the 7th minus 2x squared plus x minus 3y plus z. This one actually has three different variables. So it has an x, it has y's, and it has a z. Then of course there's the other x's and y's here as well. But there's three different letters, there's three different variables. It is a multivariable polynomial. Okay, moving down to the green, the like lower left. So it's kind of green. Okay, so the lower left, you can see it's titled constant polynomial. A constant is another word for a number that is not being multiplied by a variable. So because it's not being multiplied by a variable, it's constant, meaning it's not changing. So like, for example, if I take, let's take this 3x squared term, depending on what x is, the value of that term would change. Like if x equals 1, that's different than if x were equal to 2. But like for this number, 3,254,722, it's not being multiplied by any variable. There's nothing that's going to change it, so it's constant. It maintains the same value. So this would be called a constant polynomial when you just have a constant term, just a number without a variable, like 3,254,722 or negative 17. And then moving down to the lower right, the yellow, so these are all, they're called counterexamples. So when something is not a polynomial, and we just want to like kind of pay attention to why it's not a polynomial, because it's important to be able to recognize that so that you can find ones that are or not. Okay, so looking at this like expression right here, negative 6b to the 3/4 power plus b minus 1. So one of the rules, the first one, no, second one, sorry. One of the rules from up above of polynomials is that the exponents of variables must be whole numbers, which means no fractions and no decimals. But right here, we have a exponent over the variable b that's 3/4, which is not a whole number, it's a fraction. So that breaks the rule. So that's what makes it not a polynomial. And then if we look at this one right here, x squared over y. If we look at our third rule, that said if the terms of a polynomial include a fraction, so this is a fraction, there cannot be a variable in the denominator. And we have a y in the denominator, so that breaks the rules because we had a variable in the denominator. So that would make it not a polynomial. And then for the last one, 16 minus z to the negative third power. To go back up to our first rule for that one. So our first rule said exponents of variables cannot be negative, and we had a negative exponent right here over a variable. It was negative z or minus z to the negative third. That negative third makes it not a polynomial because it's a negative exponent over our variable. Okay, so moving down to the next example. So now we just want to practice identifying parts of a polynomial and kind of going through and like defining those parts, because I know like you hear them read out loud sometimes or like hear them in like, I don't know, lessons and stuff, but it's helpful to have the definitions for you to reflect back to. So identify the following parts of the polynomial x cubed plus 6x squared minus 9x cubed plus 1/2 x minus 11. So first we'll go through and find each individual term. So remember that terms are like separated by plus and minus, and you can leave yourself a little note of that. I'm going to zoom in a little bit and add that note down here. So for terms separated by plus and minus. So then now if we go through and we find each term, so this is one, and sometimes it's maybe helpful to like kind of point out where the plus and minuses are. So there's that x cubed, and then we have next our 6x squared, And then the 9x cubed, because it has like a minus in front of it, we just have to keep in mind that that's a negative term, like that negative belongs to the 9x cubed. We don't really have to worry about that with like positive terms. It's kind of like the default. And then the next one, 1/2 x, and then negative 11. And then remember, the minus belongs to the 11. The sign always belongs to the term behind it, never the term in front of it. So like this would be a minus 11, or a negative 11, not a negative 1/2 x. So for the terms, we'll just go ahead and list them. So there's an x to the third power, and then we'll just separate them by commas. So 6x squared, that was the next one right here. And then the 9x cubed, but there was a minus in front of it, so it'll be a negative 9x to the third power. And when I say cubed, I'm saying like a 3D square. Cubed is another way of saying like the third power. So those are interchangeable. And then the next one is this 1/2 x. And then keep in mind with the 1/2 x, there is a fraction there, but it's not the exponent, and there's no variable in the denominator of the fraction. So we're not breaking any rules. And then the last one is this 11, but there's a minus in front of it, so it would be a negative 11. Okay, so for the next section for variable, variable is just like the letter, right? So if you had multiple, you would list multiple, but ours only has x. That's the only like letter or unknown that we have in our entire expression. So for our variable, it would just be x. And then if you want to, you can leave a note that it is the letter. Letter or letters, depending on if there is more than one type. Okay, so coefficients, this next one, so read it as coefficients. It's hopefully a word that you've heard, even if sometimes when you hear it, you're like, what does that mean? If you do know what it means, props. Coefficients are like the number in front of a variable. So, like for example, right here, there's a 6 in front of the x squared, so the coefficient would just be the 6. Or right here, there's a 9, but there's a negative in front of it, so it'd be a negative 9 coefficient. Right here, there's a 1/2 in front of the x, so 1/2 can be a coefficient. So the negative 11 is not like in front of a variable, so we wouldn't consider that a coefficient. It has to be in front of the variable. There's a different word though for that negative 11. We'll get to next. And then all the way back at the front, this like x to the third power, it doesn't have a number in front of it. So if there's no number in front of it, that means that the coefficient is 1. So our coefficient would be 1, and then we'll just list those in order. So first would be 1, then 6, then a negative 9, then a 1/2. Okay, and the next one, the constant term, we've talked about this. We talked about it like at the very beginning. But the constant term is just the term without a like variable attached to it. So it's just a number, basically, a number that's completely by itself. Oops, sorry, trying to get the yellow back. It's just a number that's completely by itself. So in this case, that's the 11, negative 11, because we have the minus in front of it. So the constant term is negative 11. And then for like terms, those are terms with the, oops, I actually forgot to kind of like define coefficients and constant terms, so I'm going to go ahead and add those in now. I would add them to your notes as well. For coefficients, it's the number in front of the variable. And then for constant term, it's the number without a variable. And then like terms, the last little one, those are terms that have the same variable and exponent. So same variable and exponent. And sometimes expressions have like terms and sometimes they don't. Just depends on the problem. So same variable and exponent. Out of all of the options or all of the terms that we have from our expression, there's only one pair of like terms, like one that have the same variable to the same exact power. They all have x's, but there's only two that have the same exponent, and it's the x to the third power and the negative 9x to the third power. So we'll list those. So x to the third power and negative 9x to the third power for our like terms because they both have x and the third power. Both have to be the same. Okay, so that's it for 16.1. We're going to go to 16.2. So 16.2 is adding polynomials. There are two different techniques that you can use to add polynomials. I have zero preference on which one you pick. You can pick whichever one works best for you. So I'll show you both. The first one, example one, is for horizontal addition. The second one will be vertical addition, and then after that you can decide between the two. So for horizontal addition, we have two polynomials that are separated by parentheses, but when you're adding, the parentheses don't make any difference. So we can just go ahead and rewrite the problem without the parentheses in them. So I'm just going to copy everything down, just take off the parentheses. So it'll be a 5 plus 6x squared minus x to the third power. Sorry, 5 plus 6x squared minus x to the third power plus 7x to the fourth. And then bring down the plus sign, don't forget that. And then the second set of like terms that were in the parentheses, negative 2x to the third power plus 5x squared minus 2x plus 1. And as you get more comfortable with these problems, you can maybe skip this step, but it's something that does come in handy once you get to the subtraction section, which is 16.3. So next we're going to take a look at what our like terms are. And for this, you want to, if you have like highlighters or like colored pencils, it can come in handy, but you can definitely do it without. So I'm going to color code and kind of show you a way that you could do it with just like a pencil where it's all just kind of grayscale. So like terms are terms that have the same exponent and same variable. So like for example, I have this, I like to start with the highest exponent first. So I have this 7x to the fourth power. That's my only one of those though. So it doesn't have any like terms. So that's okay. So we'll move on to the next highest power, the x to the third power. So I have an x to the third power right here. If I'm using all one color, I'm going to put a second line to show that it's different from the 7x to the fourth. I have another x to the third power right here. I'm going to put the same like color to group those together, or the two lines to show that those are like terms, the same as the negative x cubed. And then next I'll move on to the x squareds. I have an x squared right here. So if we're using pencil, we would use like 3 lines to show that it's different. And then next I can go down to my x to the first power. I just have this one x to the first power. I'm going to put 4 lines underneath it. You honestly don't have to do anything with the ones that don't have like terms, but I like to do it so I don't forget them in the end, because I think sometimes it's easy to forget the ones that like don't have a buddy basically, and then we leave them out of our final answer. And then for the constant term, I have a 5 and a 1 that are like terms because they're both constants. Okay, so we have all of our different groups. Another way of like grouping them together or like differentiating between the different types is to use shapes. So for example, like instead of lines, you can put like circles around the x squareds and then like squares around the x cubes. Just anything that shows that they're different, and then the ones that pair together have the same shape or lines or color, whatever it may be. Okay, so now we're going to start with our highest power. So we're going to use 7x to the fourth. it doesn't have any like terms, so I'm just going to bring it down. And then next would be the negative x to the third power and the negative 2x to the third power. When you combine like terms, you add the coefficients, the number in front, and the exponents and variables stay the same. So we would combine negative 1 and negative 2. Negative 1 and negative 2 together is negative 3. And then the x to the third power stays the same. And then next is the x squared. So I have 6x squared and 5x squared. So again, I add the coefficients, the number in front. 6 plus 5 is 11. And then the x squared stays the same. It's like if I have 6 of something and then I add 5 more of that same exact thing, I now have 11 of that thing. In this case, that thing is x squared. Okay, and then we'll go down to x to the first power. So I have this negative 2x, and there's no other, just x to the first power. So I would just bring that down. So minus 2x. And then last, I have my constant terms. So those are the ones without a variable. So I have a 5 and a 1. So I would add 5 plus 1 to get plus 6 at the end. And then you always want to double check to make sure that, you got all the like terms, you have everything combined that you can, and you check that by making sure that each of your remaining terms have different exponents / variables if that's the case. So we have a 4, a 3, a 2. This would be x to the first power, and then the constant term. So they're all different, so we've simplified it completely. So 7x to the fourth minus 3x to the third plus 11x squared minus 2x plus 6. Okay, so the next method for adding polynomials is vertical addition. So horizontal was horizontal because we had it written in a horizontal line. Vertical addition takes some maneuvering of the problem. So basically instead of using different lines or different colors to show like terms, we just align them vertically. So what I mean by that is I'm just going to go ahead and I'm going to take the first parentheses and I'm just going to rewrite what's inside of it. So I'll do 5 plus 6x squared minus x to the third power plus 7x to the fourth power. And then I'm going to take what's inside the second parentheses and I'm going to write it underneath that. So I have to make sure though that I line up my like terms, the ones that are similar. So right here, first I have the constant term. So I have to take the constant term from my second parenthesis, so I'd put a 1 there. So I've put that, so I'm just going to kind of cross it off to make sure I don't miss anything. And then the next type of term that I have is 6x squared. My x squareds are right here. It's 5x squared, so I would do plus 5x squared next. And then I'm going to go ahead and cross that one off. I like crossing them off to make sure I don't miss any when I'm copying them down. And then the next spot in my vertical alignment is for x to the third power. So I would put my negative 2x to the third power next. And then cross that one off. And then my next spot is the 7x to the fourth, but I don't have a 7x, or I don't have an x to the fourth within that second parentheses. So I'm just going to kind of skip that place. The one thing, the reason it's helpful to cross things off is to recognize hey, I didn't cross off negative 2x, so I don't have that yet. So I'm just going to put that right here, and I'm not going to line it up with the x to the fourth because they're not like terms. Okay, so now we'll create one of those big addition equations with the line underneath it, and we can add each term. So I would start on the left side. I would do 5 plus 1, that's 6. And then 6x squared plus 5x squared. Remember, I just add the coefficients, the number in front. So I do 5 plus 6, which is 11. And then the x squared part stays the same. And then the next term, negative x to the third power plus negative 2x to the third power. Remember, if I don't see a number in front, then the coefficient is 1. And then I add negative 1 plus negative 2 is negative 3. And then x to the third power stays the same. And then right here, 7x to the fourth plus, like there was nothing there to add it to, so I'm not changing it. It just stays the same. I just have to copy it down because I don't have any other x to the fourth to add it to. And then right here, I'm not adding anything to that negative 2x. There was no like term, so I would just copy it down, negative 2x. And then I'm just going to rearrange this expression, oops, sorry, the answer we just got to like put it in order of highest exponent down to lowest. So that would mean 7x to the fourth comes first. So that's the highest power. And then negative 3x to the third power comes second. Next would be 11x squared, so plus 11x squared. Then next would be negative 2x. Then last would be plus 6. So 7x to the fourth minus 3x squared plus 11x, or sorry, what happened? Oh, there we go. Sorry, my 3x to the third power, I copied down as a 3x squared. So change that like second little 2 right there to a 3. Just copied down the wrong power. So 7x to the fourth minus 3x to the third plus 11x squared minus 2x plus 6 is my final answer for this. And then if we look back, notice that these two were the same exact problem. So 5 plus such and so, 5 plus such and so. All the terms were the same, so we should have gotten the same exact answer, which we did. So it's just kind of showing that, like, the two methods, you get the same answer as long as you're doing it correctly, and then you get to pick which one you prefer. I probably prefer the horizontal more, so I'll probably use it more, but like if you like vertical, use vertical. Just make sure you're getting the correct answer in the end. Okay, so moving on to example 3, this is adding multivariable polynomials. So now that we've gotten a couple examples kind of like in the bag, I want to show you a little bit of a shortcut, but you can only use it for addition. I don't recommend using this for subtraction. So for addition, the parentheses don't really mean anything. So instead of taking the time to rewrite the expression like we did here, I'm just going to kind of ignore them, or you can cross them off if you want to, but they don't change like the structure of the expression really. So this should be a longer parenthesis anyways. So we have 12a squared b cubed minus 6a minus 10a cubed b plus 10a minus 2a squared b cubed minus 14b squared. So that is definitely a mouthful. So we just want to go through and identify what the like terms are. So first I will look, okay, so my 12a squared b to the third power. I want to look and see if there's anything that has like the same exact a squared b cubed. So like this a cubed b doesn't count. Like it has the same variables, it doesn't have the same exponent, so it's not a like term. So that wouldn't be a like term. I have this like 2 negative 2 a squared b cubed over on the other side that has the same exact like a to the second power, b to the third power. So that would make it a like term because it has the same exact variables with the same exact exponents. And then I have a negative 6a right here and a 10a right here that both have a to the first power. And then I have a negative 10a to the third power b right here. There's no other ones of those though in the expression, so that would be kind of on its own, like an outlier. And then I have a b squared, negative 14b squared at the end, and there's no other b squared, so that would kind of be on its own as well. Okay, so since there's multiple variables here, it doesn't really matter if we start at the highest power, because like some are the highest power for a, some of the higher power for b. So we'll just pick whichever term we want to start with. I'm going to start by the ones that I have in green. So this 12a squared b to the third power and a negative 2a squared b to the third power. I combine them by just adding the coefficients. So I would combine 12 and negative 2. 12 and negative 2 together is 10. And then the variables and exponents stay the same. So a squared b to the third power. So I'm done with the greens. If you want, you can just go ahead and cross them off so you don't have to worry about like copying them down again or mixing them up with anything. I'm going to go on to the blues. So I have a negative 6a and a 10a. So I would add negative 6 plus 10, that's positive 4, so plus 4a, and then that's it. The a part stays the same, so that part's done. I'm going to go ahead and cross off the blues, and then there's no other like terms that I can combine, so the other ones I just have to make sure that I copy them down, I don't forget them. So like this negative 10 minus 10a to the third power b, copy that one down, I'll cross it off to mark it off so I don't like do it twice. And then at the end, there's the negative 14b squared or minus 14b squared. There's no other b squared term, so just copy that down, minus 14b squared. And then just cross it off if you want to make sure you got every single term at the end. So 10a squared b to the third power plus 4a minus 10a to the third power b minus 14b squared. So keep in mind that for these problems, there are different possible answers. So like, for example, if I had put my like negative 14b squared in the front before the like 10a squared b cubed, that's the same answer. It's still correct. There's just different orders that you can write the correct answer in. Okay, so moving down to 16.3, this is the last section. It just has two examples. We'll be subtracting polynomials. So I will say that the concept is the same as addition almost. There's one extra step, but there's a lot more room for mistakes. So we just want to be really careful with subtracting. So the first step in a subtraction problem is to change it to an addition problem, and then the remaining steps are exactly the same. So the way that we change it to an addition problem is, so our expression, x minus 9 plus 6x to the third power minus 4x squared, and then close parentheses, and then minus, we have to recognize that minus, and then 3x to the third power minus 7x plus 3. So we change it to an addition problem by distributing the negative. So what that means is that everything in the first parentheses we just copy down. So it'll be x minus 9 plus 6x to the third power minus 4x squared. So for this one, I recommend writing this step. I don't recommend skipping this in any way for subtraction. With addition, it's okay, it doesn't make a big difference, but for subtraction, it does. Okay, so the next step is to take that negative and distribute it. And we can think of it as like distributing a negative 1, because if I don't have a number in front of something, I can always say there's a 1 there. So I would do negative 1 times 3x to the third power. If you multiply a number by a negative, it changes its sign. So it changes positives to negatives, and it changes negatives to positives. So it would change this positive 3x to the third power into a minus or a negative 3x to the third power. And then next I would do negative 1 times a negative 7, so it would change that negative 7 into a positive 7, and then I would take that negative 1 and I would multiply it by a positive 3, so it would change that positive 3 into a negative 3. So notice from here to here, all the numbers are the same, but the signs are different, and that's what distributing a negative does, and that is the first step for a subtraction problem. So like this was positive, it changed negative, this was negative, it changed positive, this was positive, it changes negative. And then now it's the exact same as an addition problem where we combine like terms, we find all the ones that have the same variable to the same power. So I'm going to start with the highest power, which is x to the third power. I have a 6x to the third power and a negative 3x to the third power. I have this negative 4x squared next, but there's no other x squared, so I'll just leave that alone for now. I have an x to the first power. Remember, if you don't see an exponent, it's a first power, and then a 7x, and then I have a negative 9 and a negative 3. So I found all of my like like terms that I can group together. I'm going to start with the highest power first, which is my x to the third powers. So 6x to the third, negative 3x to the third. I combine them by adding the coefficients, the number in front. So I do 6 plus negative 3, that's positive 3x to the third. And then next I'm going to move on to my x squared term. There's only one of them, so I just copy it down, negative 4x squared. Next I'll do just my regular x's, so x plus 7x. Remember, if you don't see a number in front, then that's a 1x. So it'd be like 1 plus 7 would be 8x. And then next I have a negative 9 and a negative 3. So if I have 9 negatives and then I combine it with 3 more negatives, I now have 12 negatives. So minus 12. So 3x to the third power minus 4x squared plus 8x minus 12. Okay, and then example 2, this is the last example, so vertical subtraction, and this is with a multivariable polynomial. So it's 3a squared b squared plus 2a minus 2, and then minus parentheses 1 minus 3b plus 7a squared b squared. Okay, so the first thing we want to do is we want to rewrite it and like align it vertically. So I'm going to write everything in that first parentheses, just copy it down. So 3a squared b squared plus 2a minus 2. And then you can do this like before or after. There's a couple different like orders that you can go about this in. So I'm just going to go ahead and copy that second parentheses underneath it, like not as is, but I'm not going to change the signs yet. I'm just going to line up the like terms. So I have like a 3a squared b squared, so I should line up the 7a squared b squared with it because they have the same exact variable, it's the same power. So I would do 7a squared b squared. And then next I have this 2a. I don't have a like just a over here, so I'm gonna leave that blank. And then next I have what's called the constant term, so just like the minus 2. So I'm going to put the 1 underneath it. It's just the positive 1, so I'll put that there. And then I can't forget about this like negative 3b. I'm just going to tack that on at the end because it doesn't have any like terms from the line above to align it with. And then we'll put the line there, and then we'll put this whole thing in parentheses and put the minus in front. So we haven't like changed it to an addition problem yet. All we did was line up the like terms vertically. So now if we want to change it to an addition problem, we would change this minus to a plus. And then we would change all of these signs. So this would become a minus. There's nothing here, so that will just be like 0. This will become a minus, and this would become a plus. Okay, so one more time, I change my minus to addition. And then I flip all of my signs. So this becomes minus, minus, plus. And then now I go left to right, and I just have to add my coefficients now that the like terms are lined up. So I would do 3 plus negative 7, that's negative 4, and then my variables and exponents stay the same, a squared, b squared. And then right here, I'm not subtracting or adding anything to the 2a, so I just copy that down, it stays the same. And then next, negative 2 plus negative 1 together is negative 3. And then next, this is like there's nothing right here, so it's almost like adding 0, or it is adding 0. So 0 plus 3b will just be plus 3b. So negative 4a squared b squared plus 2a minus 3 plus 3b. Okay, so in the end, just be really careful when you're subtracting. Make sure that you're changing it to an addition problem, but between horizontal and vertical addition or subtraction, you can decide which one you